Hello, everybody. I'm really honored to be giving the 2023 Jennings Lecture on the topic of unsaturated soil behavior for the practicing engineer. My name is Jean-Louis Briaud. I'm a distinguished professor at Texas A&M University, past president of ISMGE, and past president of ASCE. In the preparation of this lecture, I have two parts, some fundamentals and then some applications. And because of the length of the lecture, we thought it'd be good to pre-record the fundamentals part so that the lecture itself will concentrate on the applications. So I will start with the fundamentals recorded in this movie. First of all, tell you a little bit where I'm located. This is Texas A&M University right here close to Houston on the Gulf Coast. And I also wanted to share with you two stories that really have influenced my career in research. The first one, you see So What here. And I remember as a young professor around the early 80s, I would go back home in France and visit with my father, who was a contractor, and I would explain to him the research I was doing, and he would listen patiently, and after about 10 minutes, he would look at me and say, "So what?" You know, and I'd be so frustrated that my father was absolutely not impressed with the work I was doing. And I remember at that time, I promised myself that whatever I did in research, I would make sure my father could not say so what. It had to be useful. And then the second story is, you see, too complicated here, was meeting actually Jeff Meyerhoff in 1986. It was the end of a dinner and at a conference, and I went to see him, and I said, Professor Meyerhoff, I'm Jean-Louis Briaud. He looked at me and said, Briaud. Oh, yes, he said, I've read your work on lateral loaded path. Too complicated, he said, too complicated. My goodness, that was another impact on the way I wanted to conduct my research. It had to be simple in the end. And so useful and simple, these are two things that stuck with me and that have impacted my research over the years. So let's talk about unsaturated soils. You're looking here at a small cliff on the Gulf Coast, silty sand, silty fine sand, and I say here 3 zones, 2 worlds. 3 zones, because if you look at those zones here, you have the water is here, the Gulf water is here. And so below this zone, the material is saturated and the water is in compression stress. In this zone here, the material is saturated still by capillary action in this case, but the water is in tension. And then if you go up where you see the lighter material here, the water is also in tension, but the soil is unsaturated. The degree of saturation is less than 1 here. The degree of saturation is 1 here. But in both those zones, the water is in tension. And so that's why I say 2 worlds. You have 1 world where the water is in tension, 1 world where the water is in compression. And so when we talk about unsaturated soils, we really mean the behavior of soils where the water is in tension. And so here's these 2 worlds. This is looking at the water normal stress. 0 stress is here. Here we have tension on this side, compression on that side. And the saturated world, if you wish, the unsaturated world and the saturated world do not correspond in terms of, so here, the degree of saturation is 1 and starts to decrease here. But this particular limit, if you wish, does not correspond to this limit here. There is a zone where the material is saturated, but the water is in tension. And then we talk about suction. And suction is a potential. It's not necessarily exercised or converted to water tension. And really what counts for us is what the state of the water is in as it impacts the stresses in the soil and deformation and so on. So I'm going to try to talk about water tension more so than suction, which, on the compression side, we talk about pore pressure. On the tension side, we talk about suction. I want to try to simplify and talk about water compression and water tension. So talking about water tension, there are two components, MATRIC water tension and osmotic water tension. You see here a typical experiment with a water container and a small glass tube, and the water rises in the tube because of the fundamental attraction between the water and the silica in the glass, SiO2. And this is the water tension that is generated by this this force T that you can see is only 72 millinewton per meter. Newton is about the weight of a small apple. So you can see that 72 millinewton per meter is extremely small, yet this is the force that creates all these unsaturated soil problems that we're facing. If you zoom in at this location here, you can see that the water is pulled up like an old sock, that's pulled up in the tiny glass tube. And so the water under this level here may be at minus 1,000 kilopascal. Yet on the other side, you have atmospheric pressure or zero gauge pressure. So there has to be a membrane between the two worlds of this water tension here and zero pressure here. And that's what is called the contractile skin. So that if we draw the profile of water stress, we have compression under the groundwater level, in this case, if you wish, and then you have water tension above the groundwater level. And then here, the water is, or the water is in tension, and you switch to the air on this other side of the membrane. And you can, just from the weight of that column of water, find out how high the water can rise in that tiny tube. And that depends on the diameter of the tube, as you can see here, given the force T that acts between the glass and the water molecules. And you can see evidence of this skin, contractile skin, because the water strider is actually making use of that skin and actually walking on water. You can see this, the skin, the membrane being deflected under the legs of this water strider. As I said, it's only about 72 millinewton per meter. And you might think, well, it's not very strong. In fact, if you're in the swimming pool and you poke your finger through the water, you don't feel any kind of resistance, because the skin is extremely, extremely thin, a few angstrom. But if you divide that force by the thickness, you get a stress that's of the order of the compressive strength of concrete. So in fact, these van der Waals forces that actually generate the existence of that skin can create tremendous stress, but it's only because it's very thin. And basically, when the water molecules are in the 3D zone of the water mass, the van der Waals forces are attracting each other, the molecules of water to each other. And when it comes to the water surface, then the molecules from under are attracting each other, but there's no molecule above because the air is there. So instead of attracting the air, the water is reinforcing the attraction that it develops between the molecules in the horizontal direction. And this increase in attraction is what actually forms the skin. The other component is the osmotic water tension. And if you can imagine this imaginary experiment where you'd have pure water on one side, salt water on the other side, and this magic membrane here that would let the water go in this direction, but not in that direction, then you could actually, and this was salt water and this is pure water, the water would actually move towards the salt water. And I could never remember as a student which way the water was supposed to go in this osmotic experiment until I realized that, you know, if I eat salt, I get thirsty. And so basically the pure water goes towards the salt water. And this difference here creates the water tension due to osmotic suction. And I talked about the water tension due to capillary action. This is probably limited to about 200 kilopascal of water tension. But when you get to extremely small particle like smectite-based particle, then that water tension can actually rise to 100,000 kPa or more. This is an experiment that was done by Mr. Garner. And he sent 3 samples at 3 water content to 8 laboratories around Texas. And he asked people to give him our measurements of water content and water tension. And you can see sample 1 here, water content. The variation in water content was quite small. That's the green bar that you're looking at. The water tension varied significantly. Most of the laboratories that measured separately on the same samples, the water tension, did that by the filter paper method, but you can see that the variation in results was significant for the water tension. If you use the log of the water tension, then the variation decreases. And fortunately, in the theoretical solution, most of the time, it's the log of the water tension that comes in play. So water tension, in a way, is much more sensitive than the water content to the state of the soil. Let's move now to effective stress. So long time ago, Terzaghi told us that effective stress was the most important stress in soil mechanics or saturated soils, and that the difference between the total stress and the water stress was the stress that controlled the behavior of these saturated soils. When it comes to unsaturated soils, from a theoretical point of view, like if you want to do numerical simulation, you have to use 2 stress state variables. To form the tensor, you're going to have to identify the sigma minus UA, where UA is the air stress, and separately UW minus UA as 2 separate stress state variables. However, again, going back to saturated soil, 1 stress variable, effective stress, sigma minus UW. In the case of unsaturated soil, so when the degree of saturation is less than 1, in most cases, 1 stress controls the behavior. That's the effective stress. But this time, the effective stress has to be expressed as sigma minus alpha UW, and alpha or chi, you know, that's the old chi factor. Alpha is the water area ratio. And so that's the way to define the effective stress, but it's not really a stress because you have here a soil property. And so you cannot form a valid stress tensor using this definition. So this is more a model, if you wish, but it's a very useful model that can actually help you to determine the strength and deformation of the soil in most cases. Collapsible soil doesn't work well, but in most cases, this stress, this model stress, if you wish, works well. So if we go back to the derivation of the effective stress in the vertical direction, this is a piece of soil, a free body diagram. We have the gravity that comes down, and at the contacts, we have the forces between the grains, and then we have the forces between the air and the forces in green between the water. And you know that you can sum forces, but you cannot sum stresses because they may not act on the same areas. So when you sum forces, you get this. If you divide by everything by the total area, then you will get total stress equal effective stress plus this area ratio times UW times this air area ratio times UA. So in essence, you're saying that the total stress is the effective stress plus this area ratio times the water stress plus this area ratio times the air stress. Now, that was the general expression, but if you look at most cases in practice in the field, then this is a case where the soil is saturated. You have the soil grain and the water fills all the voids. In this case, UW is different from zero. UA is zero because we don't have any air. And this is the Terzaghi case, sigma prime is sigma minus UW, degree of saturation is 100%. Then as the soil dry, for example, from the left to the right, the first thing that happens is air bubble will will start to appear. That's the air entry value. And in this case, when we have air bubbles in the liquid phase, then this is occluded air. The air is surrounded by water. And in first approximation, the water and the air stress are equal. And so again, if you look back from the previous slide at the general equation, then you have sigma minus UW again. So when you have occluded air, the effective stress is the same. The water, the liquid phase is more compressible, but the effective stress equation is the same. And typically this occurs when the degree of saturation is larger than about 85%. Now, if the soil continues to dry, then instead of occluded air, you have a continuous air path to the air, to the atmospheric pressure. So therefore, in this case, while the water is going to go into tension, the air pressure is connected to the atmospheric pressure, so it's zero. And in this case, sigma prime is equal to sigma minus alpha UW when the degree of saturation is less than 85%. So in the general case, the expression of this effective stress is the total stress minus alpha UW. And the in first approximation, alpha can be taken as the degree of saturation of the material. So the effective stress controls the behavior of the soil skeleton for saturated soils and for unsaturated soil in most cases. Again, as I mentioned, collapsible soils create a special problem for the effective stress. So let's look at a stress profile. So this is, we have a uniform soil here. The water level is about 5 meters deep. We have a capillary zone up to 3 meter depth. And then above this, the soil is unsaturated. The total stress increases at a regular rate. At 7 meters, unit weight being 20, at 7 meters, we're at 140. Then the water stress, but below the groundwater level, it's going to be positive or compression. And above the groundwater level, it's going to be in tension. Since this zone is saturated by capillary action, then the stress is simply sigma or is minus gamma H. And then in the unsaturated zone, the water tension increases more rapidly than the linear variation as you get closer to the ground surface. The alpha value I simplified here, 0 at the surface and 1 at the top of the capillary zone. Again, think of alpha as being reasonably estimated by the degree of saturation. And then below this capillary zone, then the degree of saturation is 1. So when we form alpha UW, then here we go, say, minus 100, and then it curves down to minus 20 at the top of the capillary zone where the material starts to be saturated. And then we have a linear variation for this component alpha UW. So by doing sigma minus alpha UW, we get sigma prime. So here we have a small value of sigma minus 100 times the value of alpha. So this is what the stress profile looks like, the effective stress profile. And so if we go to a shear strength by multiplying sigma prime 0V by tangent phi, let's say, ignoring any C prime contribution, then we get the strength profile. And you can see that this strength profile is reasonably constant in this case versus depth. Let's move to strength. So in the case of strength, we plot the shear strength versus the effective stress, but now the effective stress has its expression of sigma minus alpha UW. And when we test unsaturated soil in practice, typically we're plotting this versus total stress. And that's going to create some problems because what's going to happen is if a soil is unsaturated, because of the water tension, it's going to create a significant amount of strength. And you're going to have a C value, if you plot against total stress, that is going to include the apparent cohesion due to the increase in effective stress relying on the water tension times tangent phi. So you see the C apparent here is due to this component on the strength. So it's important to try to plot it, and it's not easy because you have to evaluate alpha through the degree of saturation, for example, and then you also have to get a value of the water tension. That's what I was telling you here, alpha effective stress parameter versus degree of saturation using data from several investigators. And you can see that alpha versus degree of saturation, there's quite a bit of scatter. So you're looking at plus or minus 30% or so in terms of precision of this rule of thumb. Khalili in Australia suggested another relationship between the effective stress parameter alpha and the suction ratio. I simplified it. Here's his expression. I simplified it the square root of the air entry value for the water tension divided by the actual water tension. So let's look, for example, at an unconfined compression test on unsaturated soil. And you can see, so I'm plotting the shear strength here versus the effective stress, sigma minus alpha UW. And if it were in the total stress, then the total stress confinement for the unconfined test is 0, and the green circle, the mole circle, would be here. But if we plot it in effective stress set of axes, the green circle is moved to the right, and because there is actually not 0 confinement, but a confinement that's created by the water tension. And so you do get the C phi or C prime phi prime equation. And if you can use that equation, and if you take a simple case of C equals 0, phi equals 30 degrees, then QU, the unconfined compression strength of that unsaturated soil, becomes equal to minus 2 UW, the water tension, times the degree of saturation. So essentially, when we do an unconfined compression test, unsaturated or saturated, the water is in tension. When you extrude it, even a sample that comes from below the water table, when you bring it back to the lab, you extrude it, the water is in tension. The total stress is released, the soil is trying to expand, and it develops water tension. And so essentially, the unconfined compression test, if you don't have a serious component of true C prime, you're measuring the effect of the water tension on that sample. Comparing saturated and unsaturated strength. If I take C equals 5, C prime, Phi prime 30 degrees, and I go down to a depth of 1 meter below the ground surface. If the soil is saturated and the water pressure is 10 kPa, let's say UA is 0, then I get a strength of about 11 kilopascal. If the soil becomes unsaturated with the same C prime and Phi prime, the same depth, and say the degree of saturation has dropped to 55%, now the water tension is at minus 250 kPa, UA is still 0, because we have continuous air path to the atmospheric pressure. The calculations show 73 kilopascal. So the strength increases dramatically when the material becomes unsaturated. And that has an impact, when you make measurements, or when you take samples in the summer, or you take samples in the winter, if there is a significant variation in the water tension or even groundwater level, then the strength is going to be significantly different. One last topic, deformation. The effect, when you look at volume change versus effective stress, in general, the effect of water tension is an increase in the effective stress and an increase in the yield stress of the soil skeleton. This is, if you wish, a typical result of a consolidation test. This one would be saturated, this one would be unsaturated. So the yield stress, or pre-consolidation pressure, if you wish, is increasing. But I found that this model is extremely useful to calculate volume change. This is a porcelain clay, and you're looking at water content versus relative change in volume. So this is the zero volume change. That's the soil as it is collected from the field, and the initial water content, in this case, about 25%. This is a free shrink test. The material shrinks on the lab table, decreases in water content and volume, and then when the particles are now touching each other and you can still lose water, but you cannot lose volume, and then the model goes straight down when you hit the shrinkage limit. On the other side, if you manage to get inundation test, then swell test, then the water content will increase, the volume will increase, and it will stop at the swell limit. The difference between the swell limit defined in this fashion and the shrinkage limit for this porcelain clay was about 24%. If you look at the bentonite clay here, then things are quite different, but still that line where the soil is saturated is aligned, is linear, and the slope is about 0.81. For that bentonite clay, the shrinkage limit is about 20%, and this is not pure bentonite. It's a mixture of bentonite and 20% bentonite, 80% porcelain clay kaolinite. And the swell limit is at 75%. We call this the shrink soil index. The amplitude is, in this case, 56%. So if you look on the left-hand side here, this is water content versus relative change in volume, and I simplified the model by a vertical line up to the shrinkage limit, and then another line all the way to the swell limit. And again, this is one of the most linear things I've ever found in soil. Turns out that the slope, which links the water content, which is associated with the water tension through the water retention curve. So if you wish, the water content plays the role of a stress, and this is the volumetric strain. So this is a stress strain curve, if you wish, and this is a linear stress strain curve. So you could think of the slope of this as a modulus, but this modulus is pretty constant, actually, because it's the unit weight of water divided by the dry unit weight. So 0.81, you know, for the previous slide. And this, if you're in gravel, you're not going to have any swelling or swell pressure. The line will be vertical. If you're in silty sand, let's say, then there will be a beginning of a swelling process. If you're in clay with low plasticity, then this swelling line will increase. And if you're in high plasticity clay, then you will have a much longer part to this thing. That's what I was showing previously. For the kaolinite, we were at 24%, and for the bentonite, we were at 56%. So if you can obtain the change in water content under a structure during the seasonal variation, then you can infer the volume change and therefore the movement associated with this change in water content. So we use this shrink swell index. Again, the difference between the swell pressure and the swell limit rather, and the shrinkage limit as a way to gauge what the potential for shrinking and swelling is, larger than 60% all the way down to less than 20%. So this concludes the fundamentals review, background overview that I wanted to do. And the next part will be the applications of these fundamentals to how this will impact our practice. Thank you for your attention. I didn't stop recording.